Okay, hello. Okay, thanks for joining this session. So today you are going to run the experiment for lab 8, okay, for embedded system lab. So today you are going to run the inverter layout and simulation. So it is to introduce to microwave analysis, CMOS 45 nanometer technology MOSFET, and also CMOS 45 nanometer technology inverter characteristic and layout in microwave. So the main goal of this tutorial is to walk through using layout based EDA tool by Microwind. Previously you used the DHCH, right? So today you are going to use Microwind, and the introduction will be accompanied with analysis of MOS transistor. So the tasks given in the lab include the familiarity and hands-on example using tool, layout design using tool, study of MOSFET characteristics, analog simulation of MOSFET, design of CMOS inverter and transistor sizing. And finally, for gate delay area and effect of transistor sizing on this parameter. So you are using the technology of 45 nanometer. Okay. And for the introduction, I think you can read by yourself. And previously you have simulated, okay, this schematic diagram, the inverter, and you know what is the circuit of the inverter, NAND and NOR. Okay, and today we are going to run the layout. Okay, so you can move to the tutorial CMOS 45 nanometer technology, and for the section A, open the Microwind 35.exe. So you can open back your previous software Microwind 3.5 DSCH, and you can open the Microwind 35. So open the Microwind 35, and you can see that this is the platform where to run the simulation. Okay. All right. So as you can see here, there are many toolbar. Okay. The component, we have the delete sound layout, copy elements, stretch, zoom in, zoom out, all, and the rest. Okay, I will explain one by one after this. And also you will have 5 component over here. 6, 1, 2, 3, 4, 5, 6, 7. 5 view, edit, simulate, compile, analysis, and HUD. Okay, so before we start, you need to open you need to open the palette. Okay, I think you can open over here. View, palette or layer. View, palette of layer. Okay, and you can see there is a component. We have contact metal poly, contact N plus difference, and contact P difference. We have contact metal 1, metal 2, and contact metal and metal 2. And we have MOS generator complex, add virtual capacitance, add virtual resistance, add virtual inductance. And also there are several layers of metal, metal 1, metal 2, metal 3, metal 4, metal 5, until the top metal is metal 8. But normally in this class, we are using only metal 1 and metal 2 as our top metal. Okay, so look at back to your, sorry. Okay, look at back on this manual. So everything I already described over here. And you can go to this step-by-step simulation. Select the Foundry using the file select and Foundry. Okay, and here you can go to this files, select Foundries. You can go to experiment 7, Microwind, and Microwind. Inside the Microwind folder, rules, select 0.45 rules. Okay, for 0 CMOS 45 nanometer. Okay, so after you already open it, okay, so now you already select the CMOS nanometer. Okay, you can select on this save as, and you can put it as this folder, inverter, inverter 000, for example, and then you click on save. So this is the compulsory step you need to follow. Okay, number one, select the Foundry. Okay, you click on the selected Foundry, CMOS 45, and save. This is the first two steps you need to follow. Okay, and next, after that, you can go back to this manual. Okay, after you have done this one, okay, you can save a design 01. Okay, for me, I put 000. Okay, doesn't matter. And all right, so now you want to design your uh, PMOS and NMOS. Right. So in 45 nanometer technology, where lambda is 20 nanometer, 0.02 micrometer, the minimum size is 0.02 micrometer for the length and 0.04 micrometer for the width. And next, create an NMOS by using the NMOS generator button. Create NMOS by using the NMOS generator button in palette. Okay, so here you can design, okay, in palette, you can design the NMOS, or you can select on edit, you can go to generate and select NMOS devices. Okay, layout generator and select the NMOS devices. And what you need to follow here, then do the same for PMOS. Okay, okay, you need to follow the same for the PMOS, but now we start to design the NMOS 0.08 the W over L and 0.04. Okay, normally when we use the 45 nanometer, so that's mean the lowest length is 0.05, or the compatible value is 0.04. Okay, for the length. Okay, 0.04 and 0.08. So the width is 0.08 and your length is 0.04. Okay, and then after you have designed it, you can click on generate device and click on here. Okay. All right, after that, you need to follow the same step for designing the PMOS. Okay, for PMOS, you are using 0.12 and 0.04. Okay, edit, generate PMOS. Okay, 0.02. Sorry, I forget. 0.12. 0.12 and 0.04. Okay, and click on generate device. Right, so this is your PMOS and this is your NMOS. Okay, you can click all, select all to view all the area. So now you already have this one. Okay, after that, after you already designed this, go back to the manual and you can set the width and length of MOS by typing in the field width MOS and length MOS either in micron or lambda unit. Okay, click on generate device tab. Okay, this one you are already done. Okay, you already done here. See, so this is the PMOS on top and the bottom is NMOS. All right, after that, after you have done this part, you need to do the well tab and substrate tab. Okay, so based on this figure for PMOS, we are going to draw the well tab. Okay, the well tab. This consists of an N-type diffusion region, an active and N-select, and a contact. In the case of the NMOS, we don't need to draw a well because the substrate is already P-type. Okay, so the device is already isolated by PN junction as long as this junction remains reverse bias. We can ensure this by drawing a substrate tab to tie the substrate to ground. All right, physically in this experiment, there is no well tab and substrate tab, but you need to add it manually. Okay, so number one, this is step number one. So for the PMOS, select contact N plus and place beside the PMOS device. For PMOS, select and plus division and cover the contact and plus. All right. So PMOS contact and plus. Select this contact and plus. Okay. Contact and plus, and you need to place it over here. Okay. All right. And then you need to enlarge the. This is what we call the diffusion layer. And plus diffusion layer. So in order to select this point, maybe you can click on this. You can disable this layer. Okay, disable this layer and also this layer and also the metal one layer. See, so you already disable the N division layer, P division layer, and metal layer. So that means you can know exactly the exact layer you need to draw. Maybe if you disable this NWL layer, that means you already disable all this layer. Okay, now we want to enlarge this layer. So you need to click on this. So you can select this stretch and move, and you need to reduce the landscape here, and you can enlarge it. So maybe it cannot because of you already enable, already disabled, and now we enable the NWL layer. So click on this stretch and move, and you can enlarge it. Okay, and after you enlarge it, you need to extend the metal one layer. This is the metal one. You cannot click on this because of it is distracted by this NWL layer. Okay, division layer. So you can now you can draw. I think. See. So you already enlarged the metal one layer. Okay. All right. So after that, here, what you need to do is go back to the layer over here. Select for NMOS. Do the same like one. Substitute contact N plus to contact P. Okay. Substitute the contact N plus to the contact P, and covered by P plus diffusion layer. All right. So here, contact the P plus P over here. Okay, and next you need to enlarge. Okay, you already enlarged, and you need to cover with the P plus diffusion layer. P plus diffusion layer here. So you need to cover all of this. Okay. Okay, after you have done, now you can connect it, the disconnected part. Okay, this one we can consider as a output. Okay, this one is your V impulse or your input. Okay, and next you need to draw the VDD and VSS. Click on metal one, select this one. Okay, so this is your VDD and this is your VSS. Okay, after you have done this part, you can click on the, okay, go back to the manual. Okay, now you need to label it. Okay, you need to label it. So this one we label as our VDD. And also we put VDD over here. Okay, this is for input at the clock over here. Just assign. And for the output is over here. Click on this area. Okay, and click off output. You can name as output. And click off assign. And after that, this is your ground. Where is your ground? Should be ground here. So after you already put all these components, okay, in this design. So now You already put everything over here. Okay, and you already put all the VDD over here. So VDD you must put as 1 volt. Okay, 1 volt. Assign. Number 2 is VDD, also 1 volt. This is your N well 3, and this is your input. Everything should be, you should follow all this step. Okay, after you have done, you need to run the DRC check. Design rule check. Design rule check, the purpose is we want to make sure everything we follow to the correct technology, correct rules. So click on DRC. So there is no DRC error. See? No DRC design rule, partial DRC due to protected layers in the palette. So that's mean you can run your design. Okay. Let's say if there is an error, for example, okay. For example, there is an error. Maybe this one I make it near to this metal one. So you can click on DRC. Okay, no design rule check. Okay, no problem. Maybe if you have error, okay, you can, for example, you click on this M plus and you put over here. Okay, click on DRC. Also no error. Okay, no error means everything is follow the correct uh, everything is follow the correct protocol, correct rules. Okay, maybe I need to delete this part. All right. So we need to add one more time the VDD. Okay, sometimes you will see the error, right? But now I want to create an error, but still no error. Wait, so maybe you can try this one. See, there is an error over here. So what is the error said? So that's mean this area you should be less than 0.24. Okay. Okay. So since you already have this error, so that's mean you need to fix this error. For example, here you need to delete all the component over here. You need to delete this one. Okay, you need to draw one more time. Okay, so design rules need detected. So we still have the error. See, there is a measurement over here, 0.6. Maybe you need to reduce it. Okay, we still have the same error over here. So what you can do here, I advise you can redraw one more time. Okay, redraw, 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 redraw. Okay, you can redraw one more time. Not the right. So you need to create another one, generate NMOS over here. Can select 0.08 and 0.04 and you can put it over here. Okay, and next you can put it one more time. Uh, you need to reconnect again, VSS. and this is the output. Okay. All right. So after that, you must put the P division over here. And you need to put the, previously we put the N plus and P contact P over here. Okay, and click on the RC. Oh, so maybe we need to adjust one more time. Okay, maybe we can move over here. Okay, and we can create one more metal line. Okay, and we can select the PMOS, put here. Okay, the RC, no design reject, and PMOS. Oh, maybe you cannot put this PMOS area. So maybe only this point. Okay. So after you have done, so since no design error, you can click all, select all, and you can click on this simulation, run the simulation. Okay. So now your input is 1 and your output is 0. Your input is 0, your output is 1. Your input is 1, the output is 0. So this is how you create the simulation. So you can click on more, okay, to see the result. And also you can click on maximum and the frequency, and you can click on reset. So they will calculate for you the speed of your inverter, 10.54 gigahertz. Okay, 10.54 gigahertz is simulated, and the time is 0.095 nanosecond. So the power distributed over here is 0.959 microwatt. Okay, so this is the basic step, okay, of your simulation. So after you have done this point, okay, now at this tutorial you can see that there is a assignment. Okay, before I set the assignment, DC analysis VTC, which is you need to obtain this graph. So in order to obtain this graph, we click on the simulation and click on this voltage versus voltage. See? Right. So here your obtained graph is around 0.5314. So that's mean you put the input of your voltage is around 1 volt, right? This is 1 volt. So it should be half VDD over 2. VDD over 2 means that you are at optimal value, which is your result is correct or optimal. Okay, you should obtain this graph. Right. So now we talk about the exercise. Right. So basically, you have done only one inverter, correct? You already create only one inverter, but now we have 1, 2, 3, 4, 5 inverter. Okay. You need to create only one inverter. All right. So this is to already create one inverter, correct? So you need to add 1, 2, 3, 4, 5. So you should have 5 inverter. So here, what you can do, you can copy all of this. 1. So you can copy 2. Okay, you should align properly. Oops. So we can use this one, we can remove and create one more time. Okay, you can create one more, should be 5. So the next, you need to know exactly how to connect the layer. So this one, the output is connected to input, is connected to input, is connected to input, and this one should be connected to input. So from here, where is your input and output? This one, right? This one and this one. So from here, what you need to do, this input will be connected to this output, will be connected to this input. All right, so this is the tricky part you need to understand. All right, so before I jump to this input and output, you can move, okay, you can combine all the VDD. Can combine all the VDD, can combine all the VDD, can combine the VDD, okay, and you can combine the VDD and also the VSS, right, and select for DRC. So there is no design error. Okay, now the point is we want to, okay, we want to combine, okay, we complete the circuit. So what you need to do here, this output will be connected to this clock. Okay, so what you need to do here, you can create this metal one to this polysilicon. Okay, or this one 10 gate. Right, so in order to connect it properly, this connected the tie aluminum gate and also this metal one, you need to find the via. Okay, contact metal and poly, or you can go to the edit, generate, create a via. Oh, there is no here. What happened to the metal bus? No, I think you can use this one. Contact metal to poly. Okay, metal to poly. And you can paste here. Okay, metal to poly. No design row error. Okay, and I think you can copy all of this. Oh, you cannot do like that. So you need to design properly. Okay, you need to do the same. Do the same. Okay, I show you one more example. This one should be attached here. Click on DRC. No design rule. Okay, so if you not put the this contact metal and poly, that means you will observe this connection between this metal and this metal, because this is the different metal. So you should contact with this via or metal to contact, or if you want to use another metal, you can use metal 1 and metal 2. Okay, if you have different metal 1 and metal 2, you should use this contact, and you have different metal to metal 2. Okay, meaning that it should be contact between two different layers. All right. Okay, so after you have done, So I think better I finish all lah to see the error, or we got the result. So we don't know. Okay. Put here. I see no design row. Very good. And select here. Okay, very good. So I think we have one more last step, which is we need to connect from this in the output to this input. So what you can do over here, this output, you can use this input method, and you can create another one, and you can create another one. Okay, you can create another one, and you can connect to this one. Okay, you can put it here. Right. So I think you have done all of this. So maybe you need to remove all the components of output. So this one no need, this one no need, this one no need, this one no need, this one, yes, we still need this one. Okay, and also this one no need, clock, clock, and clock. Okay, BDD and VSS, I think should be no problem. So make sure you draw beautiful, okay, and there is no error, the most important thing, and click on this. So I think there is no result over here because they cannot call the output over here. So maybe you can generate one more time. Edit, palette of layer. Okay, we can not see the result. What happened if we remove this one? Next, we put the output over here. Okay, it seems there is no output over here. So, what is the problem? Okay, next we put the add the clock. Oh, because there is no clock over here. Okay, sign. Yes, exactly. So that's mean no need to put the output. Okay, you just put only the V pulse and try exactly. See, now you can obtain the result. Should be no problem. Okay, and this is how you draw the oscillator. Okay, but the point here, what you need to do, draw the schematic and file out inverters for the deploying process technology 0.8, 0.18, and 45 nanometer. All right, so here, now we already simulate the 45 nanometer technologies, correct? But we need to know what happened if we use the other technologies 0.8, the Foundry, and 0.18. Okay, and also the supply voltage has been reduced is 5 volts in 0.8, 2 volt in 0.18, and 1 volt for 45 nanometer. Right now we are using 1.0 in 45 nanometer. Okay, so the next you need to draw 0.5 and 0.18. So you should have your table like this. Okay, previously we have this one, the 45 nanometer. So you should put your supply is 1, and what is the frequency? The frequency, what is the frequency obtained in this simulation is okay 5.19 and 0.193 nanosecond, 4.19 gigahertz. So here you can put 5.19 gigahertz. So you need to do for 1018 and 0.8, and you should put the result like this. So you can put result here. Maybe you can put like this. Copy, and you can paste here. Okay. This is for example. So you should do for this 0.18 and also for for the 0.8 micrometer. Okay. So your result should be consist of this. I want to know if you reduce the technologies, what happened to the frequency? This is the objective of this assignment. Whether the frequency will be increased or the frequency will be decreased, I don't know. So you should report on that. Okay, I think that's all for today, and thank you very much.